This is Unit 3, Section 3.2, looking at z-scores. So this is our second day of our unit. And so we've covered percentiles, which was the percent of observations that were equal to or less than our observation or an individual's observation. And so z-scores are another way that we're going to be able to compare apples with oranges and standardize a score here. So we're going to be able to find and interpret the standardized score of an individual value within a distribution of data. So a standardized value is called a z-score. And our z-score is the number of standard deviations from the mean, and it tells us what direction an observation falls. So a positive means that we're above, and a negative means we're below. So for an observation X, this is the formula for calculating our z-score. So z is going to equal our observation minus the mean. So that tells us how far we are from the mean, divided by standard deviations. So this tells us how far we are from the mean measured in standard deviations. So for example, given the following data set with an average of 2.7, so here's our mean, and a standard deviation of 1.9. So here's one standard deviation, two standard deviations, same direction here. Going down below, one standard deviation, two standard deviations. So here's our data inside of this. I've just drawn in those bars to kind of show you where we're capturing the data. So if we look at the observation 4, so maybe this observation here, we could say that it's about maybe 2/3 standard deviations above the mean. So if we look at that, we could say it's not all the way one standard deviation. That would kind of be 4.5. So maybe 2/3 standard deviation here above the mean. So we would have a z-score that's positive because it's above. And maybe the decimal, we would say it's decimal or 0.677, not decimal. 0 is down here. Okay, so it's going to be about how many standard deviations below the mean. So it's more than 1 and maybe 1.5. So it's 1.5 standard deviations below the mean this time. So its standard deviation, z-score, is going to be negative because now that's indicating it's lower than our average, 1.5. And so this is kind of just eyeballing what it is. We could actually calculate that by taking the 4 that's observed minus the mean that is known and dividing by the standard deviation, which is 1.9. So if I calculate this, I'm going to take 4 minus 2.7 and then divided by 1.9, and it gets 0.68. So eyeballing it, we were at 0.67666666 kind of idea, and if we calculate it, we're at 0.68. So even eyeballing it, we're pretty close on there. If I did the same thing for 0, I would have 0 minus 2.7, lost my decimal, divided by 1.9. So now I can see that I'll get a negative numerator, and divide by that 1.9, I get negative 1.42. So again, just eyeballing it, we're able to kind of see where that standardized score is. It tells us how far it is in standard deviations. So our next example, it says, given the test scores of 25 statistics students again. So these are the same scores that we looked at last time. Let's calculate the mean and standard deviation using our calculator. All right, so I'm going to pull my calculator up here, and I've entered my data into list 1. And so I'm going to use one variable stats to find the mean and standard deviation. So I'm going to go to edit, and I've entered in my scores here. So then I'm ready to calculate one variable stats on list 1 and find that we have an average test score of 80 with a standard deviation of 6.06. So I'm going to go ahead and round that to 6.07. So we have a standard deviation and mean of 80 and a standard deviation here of 6.07 when we round it. So here's what we can find on our calculator. The new part here, calculate and interpret the z-score for the following students. So what would Jenny's z-score be? We would take her observation of 86, subtract the 80 to see how far she was from what we expected on average, divided by 6.07. So if I go ahead and put that in my calculator, I get 86 minus 80, so I get 6 divided by 6.07, and I get 0.9884, so I'm going to go ahead and round that to 0.99 for my z-score for Jenny. And so my interpretation, we would say Jenny, maybe we're going to say her score is almost 1 standard deviation above average. So as we look at Jenny's score, she did better than average, but she's about 1 standard deviation above average. Katie scored a 93, so let's see what her standardized score is. So I'll take 93 minus 80, still going to get a positive numerator because she did better than average, and then divide by that standard deviation. So Katie's score here, when I put it in my calculator, so 13 divided by 6.07, I get 2.14 as my z-score. And so the z-score here, interpreted, I would say Katie scored over 2 standard deviations above the mean. And so as we're looking at this, we already knew that yes, 93 is better than the 86, but we would just be able to say it by 7%. Now we're able to say it's almost 1 entire standard deviation better, or even more than 1 standard deviation better. And if these were 2 different tests, we could actually compare a chemistry test to a PE test. And it allows us to compare on the same measure as standard deviations, but it takes away the context too. These are now just standardized scores that any number can compare. So then we have Norman, who got the 72. So now if I take Norman's score of 72, subtract 80, and divide by our standard deviation, Norman's score is going to be negative because he has scored lower than the average, so he's going to have negative 1.32 for his standardized score. So now we can say his score is about 1.3 below the average. So about 1.3 standard deviations below the average. And so as we're looking at this, we can already tell when we have 86, 93, and 72. It's not hard to rank them and say, okay, we have Katie, then Jenny, then poor Norman. But when we're looking at it, we can standardize and tell them how they did relative to the rest of the class too. When we report this as 0.99, we not only know where she stood compared to just the other 2, or where she is in relativeness to the rest of the class. So that's a kind of a bigger idea there too. And so if we look at the given blank number line here without any observation dots marked, let's write a J where we might expect to see the observation for Jenny, a K where you might expect to see the observation for Katie, and N where you might expect to see the observation for Norman. So K, okay, so she had a z-score of 0.99. So this is going to be almost 1 above here. So I'm going to put K here. Or I'm sorry, I think that was Jenny. I had that backwards. Let's put J here. And then Katie was 2 points 1, 4. So we're going to go 1 standard deviation, 2 standard deviations, and put K here. And then we have poor Norman. He did 1 standard deviation and almost half below the average. So as we compare them this way, even though we had a 72, an 86, and a 93, it allows us to kind of see the spread from 72 to 93 based on the standard deviations there as well, where we had an average of 80, and each one of these standard deviations was 6.07. So we change our measuring scale to not by ones, just kind of giving that spread. Now we're changing the spread to a standardized standard deviation. So if we had Simon had a z-score, so we don't know what his observation was, but we know his z-score was 0. What does that mean as far as his actual observation? And so when we think of a 0 z-score, that means the observation had to equal the average. I don't know what just happened there. All right. So if we know the observation has to equal the average, and we know this 80 is the average, it means that Simon was the average. He scored that 80% on the overall test. So another interesting part would be now if we move to a chemistry test. So we know how Jenny did on the statistics test, but now if we have a z-score of 1.5 on the chemistry test, did she do better in statistics or chemistry relative to the class? So this is her chemistry, and if we bring back her statistics score, she had a z-score of 0.99. So even though we don't know what percent she had here, and we know she had an 86 percent here, we can actually compare her chemistry to her statistics class. So when we compare that, we can say Jenny did better in chemistry relative to the class because she has a higher z-score in that class. So I'll write that out for us. Jenny did better in chemistry relative to the class because her z-score is higher. It is possible that she has a higher z-score here, but a lower percent. So it's possible that on the chemistry, its average might be something lower than the average on the statistics test. And then when we go 1.5 standard deviations, this still could be lower than 86% because we don't know those two things. We don't know the observation for her chemistry test, and we also don't know the standard deviation or average on that test as a whole. The only information we have is the 1.5 z-score. It is perfectly okay to have z-scores be compared even if numerically or their raw scores are not going to be compared the same way. So it's possible that the class average on this was a 60. Like maybe the chemistry test was really hard and people did poorly on it. And maybe they didn't have a lot of variation. So we only went up, maybe 4.1, and now we're only up half of 4.1. So even though she might have only had a 66% on the exam, okay, yes, that's worse than how she did on the score here, statistics test. But overall, relative to the class that she was taking, this was going to be the better score because of how it was relative to the class. So that's kind of like where I think about, sometimes you work really hard for a certain grade, and that might mean something different. For instance, when I was in school, I know that I had to work really hard to maintain grades in like my English class, but I might not have had to work so hard in some of my electives. So comparing those A's that might not be the same comparison. If I standardized it, I would see that lots of people were probably around the zero observation, right around the average as an A in an elective. But it would be unlikely to be in an English class or a core subject sometimes and have that larger, more unusual Z-score. So kind of keep that in mind, that it allows us to now compare relative to the class here. So our example to finish out, it says, the single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961. Mark McGwire, with some steroids, hit 70 in 1998. And Barry Bonds, also with steroids, hit 73 in 2001. In an absolute sense, absolutely. Well, absolutely. Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this might not be true. Baseball historians actually suggest that hitting a home run has become easier in some eras than other. This is due to many factors, including the quality of batters, the coaches, the quality of the pitcher, hardness of the baseball has changed, dimensions of certain ballparks, and the possible use of performance-enhancing drugs. To make this a fair comparison, we should actually see how these performances rate relative to the other hitters during that same year. So let's calculate the standardized score, so that's our Z-score, for each player and then compare. All right, so we have the great Bambino here. We have, Bob, here we go. So we're going to take Z-score. He had 60 home runs in his season that he did that. The average home run hitter was 7.2 and a standard deviation of 9.7. Then we have Roger Maris. Okay, so if we look at Roger, his Z-score would be 61. And on average, people were hitting about 18.8, but that varied by 13.4. And then McGwire, we had an observation. He hit 70 home runs. And on average, again, it's improving, but it has less variation there. And then the last one, we have Barry Bonds. And he hit the 73 home runs, average of 21.4 in that season with 13.2. And so each one of these relative, obviously, yes, 60, 61, 70, 73. This is the idea that, yes, the home run number has improved. But relative to each year, were they as much of a standout compared to everybody else? So if we look at Babe Ruth and calculate his Z-score, he is at 5.443. Okay, and then I look at Roger Maris, and his Z-score is 3.149. And McGwire's Z-score, and I look at 3.88. And Barry Bonds is 3.9. All right, so if we were to rank these relative to the years that they made their home run record here, we have a clear winner that Babe Ruth did something phenomenal in his year and his season. Not only did he score 60 home runs, but that is 5.443 standard deviations beyond what other people were doing. And then we'd have kind of Barry Bonds here. Again, he's doing a phenomenal thing. There were not a lot of people doing that, but he would be ranked second. Then Mark McGwire, and then we would have in the last place Roger Maris compared to the rest of the groups. These men did phenomenal things for baseball. And as far as getting people excited again in 1998, like when Mark McGwire was with the Cardinals, it was a huge thing. It was also this huge idea of the performance-enhancing drugs, but it got people back watching baseball too, or more people. And so this allows us to compare the relative home runs here. And so one of the things that we want to see is that Babe Ruth did so much better relative to the year he had hit the most home runs. That's why he is just so widely known. In 2001, okay, so the same year Barry Bonds hit his 73 home runs, Arizona Diamondback Mark Grace's home run total had a standardized score of negative .048. All right, so here's his Z-score. He is not on the same level as these gentlemen. Interpret this value and then calculate the number of home runs he hit. So we could say Mark hits .048 standard deviations below the mean in 2001. And so if we wanted to figure out how many home runs he actually had, we have our formula that is observation minus mean divided by the standard deviation. We know his Z-score is negative .048. We have an unknown variable here. We don't know what his observation is. But for 2001, we do have the average. That's the same average that Barry Bonds had. So 21.4 and the same standard deviation here. And so we're going to go ahead and solve using our algebra skills, getting x by itself. Okay, so I would multiply both sides by 13.2 and then add the 21.4 over. So that when I calculate this, he had 21 home runs. That is still a significant number, and he was still below average. I would be proud if I got one home run, and I know that that's why they don't pay me the big bucks here, but I would think 21 in one season would be still a pretty phenomenal year. However, he was slightly below average, and at 21, and the average here is 21.4. But I would still say he was an average hitter for that year, but nowhere near where Bonds was with his 73 observations there. So we have two ways to compare relative to the rest of the individuals in our group. We have percentiles, which is the percent equal to or less than, and now we have our Z-scores, which tells us how many standard deviations we are from the average. One of the things we want to keep in mind is that anything beyond 3 above standard deviations would be considered an outlier. So all 4 of these gentlemen that were playing baseball, these are outliers. They were significantly different than the rest of the data for each of their years. They are phenomenal in their own right, but sometimes Barry Bonds, getting 13 more home runs than Babe Ruth is seen as more significant. So if they were also 3 standard deviations below the average in any of those years, that would mean that they were doing significantly worse than the rest of the teams that year or the individual players that year, and we would want to probably consider them cut from our teams. Okay, also if I went 3 standard deviations in any of these directions below, I would be a negative. So hopefully they're not getting negative points there. All right, so let me know if you have any questions, and I hope you have a good day.